the year 1300 in frozen Iceland, beside a Viking earth house, where packed turf walls must trap hearth heat against -40-degree wind seepage. The sunken floor drops the living surface beneath surrounding terrain, placing interior space below wind flow so freezing air loses momentum before entering and mixing with warm interior air. Thick turf block walls are stacked in layered sod courses, where compressed fibers trap warm air pockets, slowing heat transfer outward while maintaining consistent insulation across the entire wall mass. A stone foundation ring lifts turf walls above frozen soil, breaking moisture pathways, preventing damp ground from wicking upward into walls, while stabilizing the base against frost heave during repeated winter freeze. The sloped sod roof geometry forces snow to slide downward naturally, while remaining weight presses insulation layers tighter above interior rooms, improving thermal density and slowing heat movement through roof layers. Driftwood roof beams span short distances between turf walls, distributing heavy sod load evenly, resisting sagging, while supporting compressed roof layers that maintain alignment and prevent structural collapse over long periods. Overlapping turf roof layers are arranged like shingles, sealing potential wind paths, so cold air cannot penetrate through fiber seams, while compressive weight maintains tight alignment and consistent insulation thickness across roof. The low doorway tunnel forces incoming air downward before turning, reducing cold airflow volume reaching the interior, while length and height create a controlled microchannel that minimizes heat loss during entry. Earth-packed exterior walls act as thermal mass, absorbing brief sunlight warmth and storing it within soil layers, then releasing heat slowly into interior spaces through dense, layered turf over time. A central hearthstone ring radiates warmth gradually, transferring heat outward into surrounding turf walls, where the dense fibers store and slow energy movement, maintaining stable interior temperatures within the house. The smoke hole opening geometry channels rising warm air upward efficiently, creating a draw that pulls cooler air inward through the low doorway tunnel, while vent size regulates interior airflow and heat retention. Charred interior wall surfaces seal exposed turf fibers near the hearth, reducing moisture absorption, so walls remain drier, minimizing freeze-thaw damage and maintaining insulation efficiency throughout the living structure. Raised sleeping platforms built from timber elevate bodies above the cold clay floor, positioning occupants in warmer air layers while maintaining separation from damp soil and retaining heat around sleeping areas. The packed clay floor surface forms a dense barrier, limiting dampness movement upward from underlying soil into the living area, while also providing a firm surface supporting furniture and hearth structures. Narrow, window slits cut through thick turf, restrict wind penetration, allowing sunlight to enter at low angles briefly, warming interior surfaces while minimizing cold air infiltration into the primary living spaces. Turf wall thickness increases toward the windward side, stacking additional sod layers where storms press hardest, reinforcing insulation where exposure is greatest, and slowing wind-driven heat loss through outer surfaces. An earth berm piled against exterior walls blocks drifting snow accumulation, reducing pressure on walls, protecting turf layers, maintaining wall integrity, and preventing deformation that could compromise interior warmth. Roof sod weight steadily compresses lower turf layers, increasing insulation density beneath, slowing upward heat loss, and stabilizing roof geometry to maintain alignment under snow, wind, and seasonal load cycles. A stone hearth base separates burning embers from the clay floor, preventing heat damage and cracking while radiating stored thermal energy slowly into surrounding turf layers for extended warmth. A timber lintel above the doorway carries roof sod weight across the opening, preventing wall deformation, supporting structural integrity, and maintaining roof alignment while resisting downward pressure from accumulated snow or ice. Curved wall geometry redirects roof pressure downward into surrounding soil, distributing structural forces evenly, preventing outward bulging of turf blocks, and maintaining consistent alignment of walls with roof load above. The small interior volume concentrates hearth heat within limited space, allowing warmth to build rapidly, while minimizing energy dispersal into larger areas and maintaining comfortable temperatures across floor and wall surfaces. Thick turf fibers trap countless air pockets inside walls, forming insulation that resists heat loss outward, maintaining stable interior temperatures and slowing conductive transfer through dense layered sod materials. A stone drainage trench around the foundation diverts melting snow water away before freezing expands moisture, protecting turf walls and floor from frost heave, while maintaining structural integrity during repeated thaw cycles. Darkened turf surfaces absorb scarce sunlight efficiently, warming earth layers, which gradually release stored heat into interior space, increasing overall wall thermal mass performance during short, low-light winter days. The roof pitch guides wind upward along sod surfaces, reducing lifting pressure on turf edges, preventing layer separation, and maintaining the roof's compressed insulation while supporting heavy snow loads above rooms. Interlocked turf blocks stagger seams between layers, preventing straight gaps, stopping wind infiltration, maintaining consistent thermal insulation, and holding structural alignment through repeated freeze-thaw cycles affecting roof and wall materials. Centered hearth placement spreads radiant heat evenly across floor space, ensuring surrounding walls warm uniformly, stabilizing interior temperature gradients, and allowing thermal energy to penetrate the dense turf wall mass effectively. A thick earthen roof core beneath sod blocks wind penetration through mass, stopping airflow from entering interior rooms, while compressive layers maintain insulation consistency and prevent cold drafts from undermining warmth. The stone wall base resists rot where turf meets damp ground, preserving structural integrity at contact points, preventing soil moisture from weakening lower walls, and maintaining the overall thermal performance. Sunken walls reduce exposed exterior surface area, limiting contact with cold moving air, slowing convective heat loss through wall faces, and increasing interior thermal retention across floors and wall layers. Narrow interior passages restrict airflow between rooms, slowing drafts, limiting cold air movement through living spaces, and ensuring heat from the central hearth remains concentrated where it is most effective. The heavy sod roof presses downward continuously, anchoring walls, resisting wind displacement, stabilizing turf block layers, and maintaining compressed insulation that preserves warmth within the interior structure during winter storms. Hearth ash layers accumulate around the stone base, adding insulation, retaining warmth longer within the core, spreading heat gradually to surrounding turf walls, and maintaining a more even temperature across floors. Turf roof vegetation roots bind sod layers tightly together, preventing slippage during repeated thaws, maintaining roof alignment, preserving insulation density, and stabilizing the overall structure under seasonal freeze-thaw cycles. Low ceiling height inside the earth house keeps warm air near occupants, concentrating heat from the hearth in the inhabited zone, while limiting convective heat loss to upper roof layers. Earth walls slowly release stored heat after the fire fades overnight, radiating energy gradually into the interior while dense turf fibers delay conductive loss through wall layers. Stone thresholds block direct contact between cold ground and the doorway, preventing conductive heat loss from interior floors while maintaining tight alignment between walls and entry structural elements. Turf wall curvature deflects wind flow around the structure, reducing direct impact on sod surfaces, distributing pressure along layers, and minimizing drafts that could penetrate interior spaces. A packed soil roof core thickens insulation beneath sod layers above, compressing air pockets, stabilizing thermal mass, and slowing heat transfer outward while supporting roof load from snow accumulation. Small hearth fuel loads maintain steady radiant output inside the room, avoiding overheating walls, sustaining slow heat transfer into turf, and preventing sudden temperature fluctuations in interior spaces. Turf block seams are staggered, preventing straight wind channels through walls, maintaining insulation continuity, slowing convective airflow, and preserving thermal performance across exposed exterior wall surfaces. Earth berm height is increased on the storm-facing side of walls, blocking drifting snow, distributing pressure, reinforcing windward insulation, and preventing erosion of turf layers during winter storms. Thick roof mass dampens interior temperature swings between day and night, absorbing heat from the hearth, storing energy in dense sod, and releasing warmth slowly through roof layers. Stone hearth chimney lining resists cracking under repeated heating and cooling cycles, protecting structure integrity, maintaining efficient smoke draw, and preventing damage to surrounding turf and clay materials. Low exterior profile reduces wind leverage against the structure during gusts, lowering lateral pressure on walls, preventing roof uplift, and preserving alignment of turf layers throughout storms. Turf walls are repaired seasonally, replacing loosened sod blocks promptly, restoring insulation continuity, maintaining compressed density, and preventing gaps where wind could infiltrate and reduce interior warmth. Hearthstone placement is carefully arranged to prevent sparks from igniting nearby turf layers, reducing fire risk while allowing concentrated radiant heat to distribute into walls and floors. Roof sod thickness is adjusted after snow compression each winter season, restoring insulation density, maintaining uniform load distribution, and preserving thermal performance across the roof surface. Interior wall smoothing reduces airflow pockets that trap cold air inside spaces, improving convective insulation, stabilizing wall surfaces, and maintaining consistent warmth across the house interior. Foundation stones are leveled to prevent walls from shifting during freeze-thaw cycles annually, stabilizing turf layers, preserving roof alignment, and maintaining continuous thermal protection throughout winter. Snow accumulation atop the sod roof increases insulation thickness during storms, adding weight that compresses underlying layers, stabilizes structure, and slows conductive and convective heat loss from interior spaces. Compressed snow layers seal minor roof air gaps tightly, reducing infiltration, maintaining insulation density, supporting roof stability, and preventing wind-driven heat loss into interior rooms. Hearth embers are banked nightly, sustaining slow stone heat release until morning, maintaining warmth across floors and turf walls, stabilizing interior temperature, and prolonging thermal comfort after fire burns. Turf wall repairs focus on windward erosion zones each season, restoring compromised sod layers, maintaining insulation continuity, preserving wall alignment, and preventing drafts that would otherwise enter interior spaces. The earth floor is slightly sloped, directing meltwater toward drainage trenches, preventing pooled water beneath walls, minimizing moisture absorption into turf, and protecting insulation layers from freeze-thaw damage. Stone drainage channels carry water away from foundations before freezing expands cracks, protecting turf walls, maintaining structural stability, and preventing concentrated ice from disrupting roof and wall alignment. Roof beam spacing is minimized to reduce sag under sod weight loads, supporting compressed roof layers, maintaining insulation density, and preventing deformation that would compromise thermal performance. Turf blocks are cut with roots outward, strengthening the wall face against wind, anchoring sod layers, stabilizing insulation, and preventing dislocation during storms or thaw cycles. Hearth smoke rises into the roof cavity before exiting the vent opening, transferring residual warmth to the roof core, drying turf fibers, and stabilizing insulation above the interior space. Warm smoke dries turf fibers in walls and roof, reducing internal moisture content, preventing freeze expansion, preserving insulation density, and maintaining stable heat retention within the earth house. Stone hearth rings store thermal mass longer than bare ground, releasing energy slowly into surrounding turf walls and floors, stabilizing interior temperature and extending warmth throughout cold nights. Door tunnels are angled, blocking straight wind paths into the living space, forcing drafts downward, reducing cold penetration, and maintaining thermal continuity across interior walls and floor surfaces. Tunnel ceilings are low, forcing cold air downward before reaching entry rooms, limiting airflow into living spaces, and preserving concentrated heat from hearth output in the main interior. Earth berms are shaped smoothly around walls, preventing turbulent wind eddies, redirecting moving air, protecting turf layers and maintaining continuous insulation and thermal stability across the house perimeter. Roof sod overlaps are oriented downhill, directing meltwater away from seams, preventing infiltration, maintaining insulation continuity, stabilizing roof layers, and preserving thermal density throughout interior spaces. Wall thickness is greatest near the ground, where cold penetration is strongest, adding thermal mass, slowing conductive heat loss, protecting foundations, and stabilizing temperature across lower wall and floor layers. Stone footings elevate turf above persistently wet frozen soil, preventing moisture wicking into walls, stabilizing the foundation, maintaining insulation integrity, and protecting turf layers from freeze-thaw deformation beneath the floor. The hearth is positioned slightly forward, directing warmth toward the entrance tunnel, preheating incoming air during door openings, reducing draft impact, and maintaining interior temperatures near occupants entering or exiting. Packed clay floor cracks are filled, preventing cold seepage through gaps, stabilizing walking surfaces, maintaining thermal continuity across the living area, and protecting the interior from frost-driven drafts beneath walls. Roof turf is trimmed along edges, keeping layers tight against winter wind lift, preserving insulation density, maintaining roof alignment, preventing sagging, and protecting the compressed sod mass above interior rooms. Hearthstone spacing is arranged to allow airflow between embers, sustaining steady controlled combustion, maintaining radiant heat output, preventing overheating of surrounding turf, and distributing warmth evenly across walls and floors. The smoke vent is partially closed to regulate interior heat retention, limiting warm air loss, controlling airflow through the roof cavity, and maintaining consistent temperatures inside the structure during long nights. Interior timber posts support roof beams, reducing deflection under heavy sod loads, maintaining roof geometry, stabilizing compressed insulation layers, and ensuring long-term alignment of both walls and roof under repeated weight cycles. The earth roof core is layered thickest above the hearth heat source zone, concentrating thermal mass where warmth is greatest, slowing conductive loss through roof layers and extending radiant heat retention. Turf wall inner surfaces are smoothed, minimizing convective air currents along walls, reducing cold drafts inside, maintaining even heat distribution, and preserving insulation efficiency across the interior space. A stone curb around the hearth confines embers, protecting turf floor edges, preventing accidental ignition, stabilizing ash accumulation, and maintaining thermal transfer from hearth to surrounding walls without fire hazards. Door flap skins are layered to reduce heat loss during frequent openings, creating multiple barriers, slowing cold air entry, maintaining interior warmth, and preserving concentrated heat from the hearth. Berm soil is compacted to prevent frost heave, stabilizing walls, maintaining alignment, preserving turf layers, and ensuring the foundation continues, supporting roof and wall weight through seasonal freeze-thaw cycles. Roof sod is replaced where rot has weakened insulation thickness over years, restoring compressive density, maintaining thermal performance, preventing gaps, and stabilizing roof alignment above interior rooms. Hearth ash is redistributed nightly across stone surfaces, enhancing thermal retention capacity, maintaining slow heat release, stabilizing wall and floor warmth, and improving consistent interior temperatures through the night. Wall turf orientation is alternated when laying blocks, locking fibers across structural joints, stabilizing insulation, preventing gaps for airflow, and maintaining consistent thermal performance through freeze-thaw cycles. Roof pitch is increased on the stormward side, shedding drifting snow quickly, preventing layer compression, reducing roof weight on walls, and maintaining insulation density under heavy precipitation. Drainage trenches are cleared to prevent ice blockage around foundation stones, ensuring meltwater flows away, protecting turf walls from moisture accumulation, and maintaining foundation and floor integrity. Hearth stones are darkened, improving radiant heat absorption and release, storing energy from embers, extending warmth distribution into surrounding walls and floors, and stabilizing interior temperatures over several hours. Interior niches are carved within turf walls, providing storage for warmed household items, preserving heat around objects, and preventing unnecessary drafts while maintaining consistent wall insulation. Wall thickness tapers upward, reducing roof load while retaining insulation, stabilizing compressed turf layers, distributing weight evenly along walls, and minimizing structural stress on the foundation beneath. Earth roof mass blocks wind whistle, reducing pressure infiltration into interior spaces, slowing cold air movement along roof fibers, and maintaining insulation density during gusts and snowstorms. Stone sills beneath doors resist wear from traffic, maintaining tight seal edges, preserving thermal continuity between interior floors and exterior air, and protecting turf and clay floor layers from drafts. The hearth is positioned below the vent to maximize smoke draw and heat spread, directing energy upward into the roof core and walls while stabilizing interior temperatures. Roof sod moisture is controlled to prevent freeze expansion, tearing layers apart, maintaining compressed insulation density, protecting roof geometry, and slowing conductive heat loss through turf layers. Wall turf is replaced before winter, maintaining a continuous insulation barrier, preventing drafts, stabilizing structural alignment, and ensuring heat retention through cold season freeze-thaw cycles. Berm slope directs surface runoff away from wall-based stones, preventing water pooling, minimizing moisture absorption into turf, maintaining insulation density, and protecting foundation stability during thaw cycles. Roof vegetation is trimmed to prevent snow pockets forming uneven heavy loads, maintaining consistent compression, protecting turf layers from displacement, and preserving roof thermal performance during winter storms. Hearth firewood is stacked nearby, reducing door openings during storms, limiting cold air influx, maintaining hearth heat inside, and preserving interior warmth across floors and wall layers. Stone hearth rim height is optimized, preventing rolling embers onto turf, protecting floors, stabilizing ash distribution, and concentrating heat transfer efficiently into walls and surrounding interior surfaces. Wall curvature is fine-tuned, balancing roof thrust into soil support, distributing pressure evenly, preventing outward bulging of turf layers, and maintaining compressed insulation along the interior and exterior surfaces. Earth floor depth is increased, adding thermal mass beneath living areas, storing heat from the hearth, slowing conductive loss into soil, and stabilizing interior temperatures over long cold periods. Roof sod is compacted manually after thaw, ensuring dense insulation layers, preserving compressed air pockets, maintaining roof alignment, and preventing thermal loss through gaps or displaced turf sections. Drainage stones are reset where shifting alters water flow direction, maintaining proper runoff, protecting walls and foundations from moisture infiltration, and preserving roof and floor integrity under seasonal freeze-thaw cycles. Hearth heat cycles gradually dry the entire earth house interior, reducing internal moisture, preventing turf freeze damage, maintaining insulation efficiency, and stabilizing interior temperatures throughout walls, floors, and roof layers. Across the Viking earth house, every element reflects accumulated responses to environmental pressures. Sunken floors, compacted clay, and stone footings collectively isolate interior surfaces from frozen ground. Turf walls, layered and curved, and overlapping sod roofs compress air pockets, channel wind, and shed snow, stabilizing thermal density while maintaining structural alignment. Small interior volumes concentrate hearth heat, while raised timber platforms elevate occupants above cold floors. Smoke holes, vents, and chimneys manage airflow precisely, allowing rising warmth to distribute through roof cores and walls. Each adjustment, thicker windward walls, tapered ceilings, compacted berms, staggered turf seams, reduces convective loss, while drainage trenches and sloped floors guide meltwater away from foundations. Roof and wall mass absorb scarce solar radiation and radiate heat gradually, while seasonal repairs maintain continuous insulation across all layers. These systems operate not as isolated features, but as interdependent components. Timber posts support driftwood beams, transferring roof loads to curved walls and foundations. Hearth placement coordinates with airflow, roof thickness, and wall orientation, creating a controlled thermal environment. Roof vegetation roots anchor sod layers. Ash layers store warmth. Stone bases protect soil and turf from repeated freeze cycles. Every measured adjustment has a direct causal impact. Weight distributes load. Slope directs water. Fiber density retains heat. The house itself functions as a material instrument, encoding centuries of observation and iterative refinement into its form and placement. Viewed across time, these adaptations exemplify a human pattern of embedding survival knowledge into durable material forms. Structures are not merely shelters, but instruments of control over heat, moisture, and wind, extending human capacity through geometry, density, and composition. Each roof, wall, and hearth preserves the outcomes of repeated experimentation, recording functional understanding in physical layers. In the quiet hours after the fire fades and winds sweep across frozen earth, the house endures not as a monument, but as a precise articulation of the interplay between human design and environmental force.